You're listening to MedX, the Medical Extrusion Podcast, presented by US Extruders. Extrude with confidence, custom extrusion equipment designed for you and your application.
Hey folks, welcome back to the MedX Podcast. Today's guest is Brett Lenz, Director of Engineering at plastics design company, PDC. PDC is a leading manufacturing partner of micro-injection molded components used in medical device and life sciences applications. The focus of our discussion today is related to overmolding and insert molding of catheter tips. Hey, Brett, welcome to the MedX Podcast.
Thanks for having me, Steve. Really great to be here.
Yeah, we did that little clip together at MD&M West, to let everybody know that it's coming, and the phone lines have been ringing. When is Brett coming on? So it's finally good to have you on. I'm really excited to talk about overmolded radiopaque tips and the different applications and the capabilities that you have in that area. And I know there's a variety of different techniques that are used to add a distal tip to a catheter shaft, and I think probably the most common is RF thermoforming, but the focus of our discussion is overmolding and insert molding of catheter tips. So I want to talk to you about that, and just kind of, if you can just, before we do that, provide a high-level overview of PDC, your background and location and capabilities.
Yeah, absolutely. So PDC is a contract manufacturing injection molder in Scottsdale, Arizona. We're a mid-sized company, been around for a little over 30 years, and more recently are on a bit of a growth trajectory with kind of new ownership with a private equity group called Vance Street Capital. Really, our emphasis is in medical molding. So we're really fairly 50-50 split between medical device molding, including catheter tips and kind of adjacent technologies in cardiovascular space, other medical devices ranging from orthopedics to diagnostics and drug delivery, things like that. A lot of micro molding type parts. We also have a lot of focus on the life sciences side. So a little bit larger parts, talking microfluidics, microtiter plates, things of that nature. Larger format parts, but with small features on them or tight tolerance features on them that require some of the expertise that comes from micro molding on a larger format part.
Okay. Good. So let's get into overmolding a tip directly to the distal end of a catheter shaft, and just kind of starting at a high level, what types of materials and diameter ranges are you typically working with when you're overmolding a tip to a catheter shaft?
Sure. Probably the most popular that we see are various grades of PEBACs and polyimide tubes are the most common. There's certainly other players out there, but those are probably the lion's share. Diameters really range. We see anything down from some of the softer PEBACs down in the kind of 25 short D range all the way up into the 70, 75 short D, and then everywhere in between. That's probably the bulk of what we see there. There's some other cases we've seen, different nylons. We've seen PEEK tubing, a few other kind of specialty cases there. But yeah, I think most of the discussion we'll have today is probably focused on the PEBACs and polyimide.
Okay. And related to those materials and radiopacity, so that you can see the tip and the catheter shaft under X-ray and fluoroscopy. That's part of our discussion as well. In that regard, what type of fillers, radiopaque fillers, do you typically work with? And maybe give us a context of loading levels as an example.
Sure. Yeah. Again, most common or lion's share there, we see barium sulfate is quite popular and gives a white color. Kind of naturally to that. So that's quite popular. Loading levels can vary, see anywhere 10, 20, probably the highest I've seen is 30%. 10 to 20 seems to be pretty common for the tip itself. And then, of course, we'll probably talk soon here on insert marker bands. So we do a lot of insert molding, radiopaque marker bands, platinum iridium being the most common that we work with here.
Okay. So kind of backing up a little bit, we're talking about overmolding onto a shaft. If you can kind of give us a little background there, and as it relates to that, curious to know the transition on the catheter shaft on the ID, for instance. Is it seamless when you're overmolding? Is there flash? How do you prevent flash? Some of these things I'd like to, if you could share with us.
Yeah, it's a really, really key question. So yeah, typically we've got the catheter shaft coming in. The internal geometry of the part will have a shoulder typically to give room for the OD of the tubing, and then ideally match perfectly to the ID of that tubing. And then we're overmolding around that. So we'll load that tubing into the tool on a pin or a hand load of some sort. That lets us get that in there. And the real money shot there is to get a good fit between that pin and the tubing and the cavity that tubing pin assembly is going to go into. That's what's really going to determine how good of a match line you have there, how seamless of a transition you have. Mm-hmm. The nice thing is, in that situation, flash is not necessarily really a major thing at play, because you don't truly have a match line of tooling surfaces, which is really good. So really we're talking about where are we controlling where the material can flow. Mm-hmm. But there's not a match line in the traditional sense. Let's say you had you weren't overmolding a tube, and you were just, say, making a connector or a transition that a tube was going to go into later, and maybe get reflowed or bonded through other means. Now that plastic part is going to be formed by two core pins that meet together rather than the tubing itself and a core pin. That situation is where you have major risk of flash, because if your draft angles are really coming from two directions, that by nature means you have two core pins that form that ID. You have an interface between the two. That's a surface you have potential to flash on. There's things you can do to control how it flashes. If you, say, had just the two pins butt against each other, you're going to tend to have that flash coming in towards the ID, occluding the ID, which is typically not what people want. You can improve that a little bit by, say, piloting the one pin into the other, the smaller into the larger. And now if it flashes, it's going to tend to flash as tube flash along, kind of extending the surface of the smaller ID. Still not ideal, could still interfere with the mating shaft later, but that might be a worthwhile trade-off in that situation. But in the case of just a regular catheter being overmolded directly, you don't have that interface anymore. So it's actually a really ideal condition for that. You don't have a surface to flash into. Rather, there, you're really down to controlling what's the position of the tubing relative to the pin, and therefore relative to the cavity, so that the end of the tubing is where you expect it to be within the tip. And you can control that through steps on the pin. You can control that through draft angles on the pin that kind of give you a stop to move up to. You can control that with a secondary fixturing that gives you a hard stop to press that tubing up on the pin to a point and then load into the tool. Or you can get really fancy and use either mechanical or optical checks once it's in the tool to confirm that you have the location.
All right, thanks. Let's move on to bonding. I know if you're working with compatible materials, PEBACs to PEBACs or PEBACs to nylon 12, not so much of a challenge, but if you're working with dissimilar materials, I suspect there's some extra steps that you need to take and maybe even utilize beyond kind of thermal bonding, some mechanical methods to bond. Can you talk to us a little bit about working with similar materials and also with dissimilar materials?
Yeah, definitely. So quite a bit to consider with it. One is kind of what is the spec that you need to achieve in terms of bond strength or kind of actual use case scenarios of separation. Probably one we see really commonly is less so of the, say, the tubing to an overmolded tip, but say a dual durometer tip where we're overmolding one durometer onto another durometer of a two-piece tip.
Yeah.
And there, what we're concerned with can be sure just straight pull force, but also deflection. If the, say, the softer durometer tip, as it bends, does it tend to start to separate where the match line between the two are? We've even gone as far as building custom fixtures to test that as an in-process inspection. Basically, just come up with a test criteria, say, okay, if we deflect with this controlled mechanism to a certain angle so many times and for so long, and then inspect and see a gap or a separation at all or of some tolerance, then we have a test criteria around that. But yeah, I think the key is having something in addition to just thermal or chemical bond between the materials goes a long way. We see, especially with those dual durometer tips, designers incorporating mechanical interlocking between them. And if you have the space to do that, you have room where, yeah, these two are just going to overlap with each other. There's going to be an interior region where the two are just forming kind of the solid mass of the tip. It can be quite simple just to put some striations or other type of mechanical features that allow the material to flow into each other and improve the grip strength.
Get some good interlocking strength.
Mm-hmm. Exactly.
Okay. Good. One of the samples that you sent me is kind of a curved tip, and it'll be on an unboxing video, which I'm excited to do. Yeah. But curious, I know tips, to have a curved tip, possibly for some kind of branch artery. I'm not sure, a side branch or to deliver a device or a drug. Mm-hmm. Tell us a little bit about these curved tip type tips and, any challenges related to the manufacturing process. I imagine using a mandrel for something like this could be a little bit of a challenge just to get it out.
Yeah. So they are challenging. They're one of the more unique tooling options that we've been able to develop expertise around. And yeah, so really within there, it's a more or less standard tip where there's an ID for lumens to move through. The manufacturing challenges with making that curved ID are high level twofold. One is just manufacturing the pin itself, and quite a bit that goes into that. In lower volume, we can do that with hand loads and then use external fixtures to remove them. And in higher volume or more robust long-term tooling, we can accomplish that with mechanisms in the tool to demold it automatically, improve cycle times, improve reliability. You can imagine down at those small diameters, that becomes quite a delicate feature. And so they are prone to experiencing a lot of stress, particularly in the hand load versions of those, because it's not as controlled as when it's enclosed in a slide mechanism. But yeah, so challenges to that come down to machining them in the first place. We use various CNC strategies to machine those and keep them supported while we machine those. So we could machine a section and use potting, and then use that potting as support and machine other areas of that, until we ultimately get a finished part that we can break out and then polish and hone into finished geometry. And then the demolding is probably the next biggest challenge with that, is making sure that we can reliably, cleanly remove that core without damaging the core itself or the part over time. Probably key considerations to that just comes down to having geometry you can smoothly pull. Probably for any folks interested in trying to do something like that, keeping a constant radius on that curvature is really key, because that's what allows you essentially any material you've just pulled past on, say, the more distal end of that, the material more proximal is going to follow that same path, so you've already cleared it. radial shapes aren't able to do that. And so that's probably the key constraint around that.
Okay, excellent. Thank you. Let's move on to insert molding. But for the extrusion folks out there, if you could tell what the difference is between overmolding and insert molding, and then we'll get into insert molding.
Sure. So insert molding we would think of as you have an already produced component, say a marker band, or we would even to some degree consider, say, a catheter tube to be an insert, depending on kind of what parlance you're trying to talk about it in.
Yeah.
But we've got an already made component and we want to insert it into a tool and then mold material over that. In a sense, that's also over molding. It's just kind of how we think about the component that we're molding over the top of. Over molding, or a two-shot part we might think of is we're going to mold one part and then we're going to mold another part over the top of that. So that curved tip we were just looking at as an example of that. There's a harder durometer proximal end piece of the component, and then there's a softer durometer tip. And we mold the harder durometer one first, and then we overmold the soft durometer over the top. That one's actually a great example. It does both. So that first substrate piece has a marker band that gets insert molded into the substrate plastic component, and then that marker band and substrate molded part get inserted into the second tool for the overmold piece.
Okay, excellent. So then let's talk a little bit more about that, where your ability to insert mold or fully encapsulate a radiopaque marker band, for instance, within the wall of the catheter tip. Share some examples or some highlights about that technology.
Yeah, on its face, it's a relatively simple idea of just, we want to embed that in a specific location in the part, because it acts as a guide to not just where the component is, but where are features on the component relative to the marker band. If a physician knows, okay, if that marker band is there, then I know my tip is this distance away from that, and kind of gives not just a sense of location, but even orientation and more precise location of the device. In order, I guess, considerations on how we get those in there and how we handle them and mold with them. They're obviously very small, and loading them reliably is a real challenge. So typically we're placing those over the top of a core pin, using the core pin to locate them on the diameter, and then using a shoulder or some other shutoff feature in the tool in order to kind of lock in where the marker band sits along the length of that pin. And that we can do two ways. Again, on the low volume side of things, in order to keep costs down on the tooling, we can do a lot of this manually. We can do this with hand loads, or we have trained operators under magnification using fixtures can load the marker bands onto those hand loads at the bench, and then either by hand or with the aid of a fixture, transfer those into the tool. The fixtures are really key to that because they help do that reliably and position things reliably. In some really extreme cases, there's no hand load component that they get to preload the marker bands onto. They're using a fixture to transfer just the marker bands by themselves straight into the tool over the top of a core pin that's fixed in the tool. And those are a little bit more advanced features or fixtures. And then the extension of that is at higher volume, and where you need more reliability long-term, you can do that robotically. And that becomes really challenging because we're now using a robot to place very, very small components with a very, very precise location. The one we were just looking at has an ID on that marker band somewhere in the ballpark of 15 thousandths of an inch. So it's literally threading a needle into the tool with that. That's
interesting. You kind of already touched. I was going to ask you a little bit about multi-component, multi-durometer. You touched on that. That can add some complexity. And then you talked about kind of scaling things. when you put all these challenges together with automation, fixtures, multi-component, are you still kind of able to achieve some pretty high process capability indexes, PPK, CPKs when you're doing that?
Yeah, absolutely. They obviously bring their challenges. Frankly, on a lot of those parts, we see more of the challenge come from the part geometry itself, or a lot of times even just flash callouts and things like that. Obviously, catheter tips super sensitive to having flash, having any kind of disruption, particularly on the outside of the tips. So we have quite stringent requirements when it comes to those types of criteria, and we often find ourselves process limited by those more so than say marker band positioning, things like that. That being said, yeah, it's all quite delicate work. They have tight tolerances that makes for tight process windows, and they oftentimes take quite a bit of work to get dialed in and reliable. Once they're there, though, that's the kind of beauty of injection molding, is once you do get a process developed and you do pull those windows and you understand what variables are at play and you're able to work around them, once you solve it, it typically stays solved unless new variables get entered into the mix. It can be very reliable long term.
Very highly repeatable.
Yes.
Okay. I was having a conversation recently with the CEO of a medical device contract manufacturer. They hired a design firm, to design a component within a catheter shaft, and the design was elegant, but when it came time for manufacturing at scale, it wasn't manufacturable at scale. Yeah. So share with us.
I was just going to say to that, yeah, we're very cognizant of that, and that's something we try to really screen for a lot in the early stages. So we do a lot of DFM work early on, design for manufacturability, even in the RFQ stage. So when we're looking at new projects, we'll put quite a lot of effort and frankly do a lot of kind of courtesy work to give advice and feedback on, hey, here's things you could do or be thinking about to improve the manufacturability of the part. And if we see things that flat out from the beginning, someone calls out a 1/10 tolerance on the plastic parts, like, okay, yeah, we need to factor in some room for variation. Hitting a dimension's one thing. Qualifying to that tolerance is a very different animal. So yeah, that's the more you can screen for that early on and have discussions about that and have kind of fit form function discussions is really what it boils down to, is to say, hey, why does this need such a tight tolerance? What's driving that? Does it need to be that? What's it interface with? Is there room to add some tolerance on the mating component, let's say? And find usually you can work through those types of obstacles.
Yeah, it's all about, kind of a collaborative effort, right? Working with the customer on something like that.
Yep.
Okay. One last thing I just wanted to talk about, and if you could talk about, is your, production quality prototyping, unless that was part of the DFM, or is that kind of separate? Go ahead. And
no, yeah, it's a really good extension. I think the point or the topic here is kind of how we approach prototyping at PDC. In some arenas, when people are thinking about prototyping or at the stage where they're doing prototyping, speed and just getting some representative part in hand is the name of the game, and that's a fine place to be. That's a very early stage thing. You need to just get down and dirty and have something you can test with. And that's really good. To some degree, we can offer that. Probably the thing that differentiates us a little bit is we take generally a little bit different tack when we think about prototype tooling. Often we're thinking ahead to the later production stage of the project. Really, our goal with the types of parts we're working with is we're trying to get our prototype parts to match the quality level and specification level that eventual production parts are going to be expected to meet, and do that at the prototype level. Just try to do that in a more cost-effective way with maybe less longevity. So we're going to generally, we build a prototype tool, If you molded a part off of that tool and then later molded a part off of its future production tool, you'd have a hard time telling them apart. They're going to be built to similar quality levels. The difference is going to come out to the prototype tool might be made out of aluminum and warranted for 20,000 shots versus the SPI 102 hardened production steel tool is going to be warranted for 1 million shots. So there's a lot more longevity to it. It comes with a lot more maintenance background and whatnot around it. But what we're really shooting for is parity between the quality level of the part. So when we're prototyping a challenging, tight tolerance, high risk medical device that needs to function well, oftentimes it's really key to find out if those functional criteria are met early on. And if you're cutting corners in the quality of the parts early on, you may not have visibility to all of that or what's feasible long-term in the production tool. If you're saying, yeah, we're going to do as best as we can get out of the geometry at the prototype stage, and that's representative of what's going to be feasible in the production phase. And if you find a problem, great. Now it's a problem. You can work on it versus, yeah, okay, that's maybe a problem just because it's the prototype tool. We take a different view of that.
Interesting. Okay. Brett, this has been a real interesting conversation. Thank you so much for joining us today and sharing your capabilities related to radiopaque, overmolded, and insert molded tips for catheters.
Absolutely. Yeah. Thanks for having me. It was nice to chat. Fan of the show and happy to get to join you.
Okay. Thanks again.
Thank you for listening to MEDX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. For video episodes, go to us-extruders.com/podcasts. All links are available in the show notes.